In this video, we're going to explore the concept of non-random mating and determine how non-random mating affects the genetic diversity of a population. And we'll be able to use the formula that Jed talked about in his lecture. The spreadsheet template is set up as follows, and let me give you a quick orientation. We're going to have a parental population, and the parental population genotypes will be established down column C. We're then going to let each of our parents reproduce according to a mate selection grid in cells E3 through G5. Once individuals have selected a mate, we're going to simulate the process of reproduction, assuming that each individual will produce just one offspring. And then along the way, we're going to calculate the genotype numbers of the parents and the offspring, the genotype frequencies of the parents and offspring, and the allele frequencies of the parents and offspring. Our key outputs are going to be the observed heterozygosity of the offspring population and the expected heterozygosity under Hardy-Weinberg. And those two values will let us compute the F statistic that Jed talked about. Along the way, we'll be able to see how changing the population size affects things, as well as how this mate choice grid affects the results. Okay, let's get started. We've set up a series of individuals down column A that begin with 0 and go to 999. And so the spreadsheet can hold 1,000 individuals, and we'll be able to enter that number in cell B2. Now, we might not always have 1,000 individuals, and so the count column, down column B, will simply return the number 1 if the individual is part of our parental population. And we'll do that with an if function. We'll find if, and the logical test is simply going to be, is the individual's number less than the parental population in cell B2? We'll anchor the reference to cell B2, and if this is true, then we'll have the spreadsheet return the number 1, and if it's false, we'll have the spreadsheet return a 0. We can press OK and copy this through, and now if we change the parental population, you should see that the count is 1 only for the number of individuals actually present in the population. The next step is to assign genotypes to each of these individuals. And we'll do that by using the cells B3 through B5. The choices are A1A1, A1A2, or A2A2. So in this situation, we're dealing with a single locus called the A locus, and individuals can be homozygous A1A1, they can be homozygous A2A2, or they can be heterozygous A1A2. And remember, each individual carries 2 alleles. And from this setup, we can see that there are 2 alleles present in the population, allele A1 and allele A2. And remember that each individual carries 2 of these copies. One was inherited maternally and one was inherited paternally. Let's enter those numbers 250, 500, and 250 into cells B3 through B5. And you can see that we've entered a sum equation so that you can double check that you have accounted for all 1,000 parents listed in cell B2. Now to assign a genotype to individuals, we're going to use the tally trick that we used in the Hardy-Weinberg spreadsheet. We'll enter a 0 in cell C2, and then we will enter the equation sum B3 through B3 and anchor the reference to the first B3. If we copy this through, then we'll see that we have an array that starts with a 0 and ends with our total population size. And what this is doing is simply accumulating the individuals as we consider more genotypes. So for example, if we start with A1, we're considering 250 individuals. If we then add on the 500 heterozygotes, now we're considering 750 individuals. And if we add in the remaining 250 homozygous A2A2s, we will have accounted for all 1,000 individuals in the population. And we're going to use this tally in a lookup function, just like we did in the Hardy-Weinberg exercise, to assign a genotype. The only trick here is that the individual must have a count of 1 to receive a genotype. So to handle that, we're going to use an if function. And here our logical test is going to be, is the count equal to 1? If it's true, then let's assign a genotype. If it's false, though, let's assign a blank, and I've indicated that with 2 double quotes. Let's go back to the true statement, the individual's part of our population. Well, now we need a lookup function that will assign that individual a genotype. And we'll do that by heading over to the left portion of the screen, finding the drop-down box and finding the lookup function, and then choosing the lookup function that has 3 arguments. The first argument is the lookup value, and here we want to look up the individual's number. We'll find that number in the lookup vector, and that's our tally column, C2 through C5. And then we'll have the spreadsheet return the result vector, which is stored in cell A3 through A5. We need to anchor the lookup vector and the result vector so that when we copy this through, this equation will still work no matter which individual we're talking about. You can see that the spreadsheet is returning in A1. And how this formula is working is it's finding the 0 in this tally, and it's really finding what it's nested between. Which 2 cells does it fall between? This function is going to find the number 0 is between these 2 cells, and it will return the bottom of those 2 in the result vector. Make sense? Hopefully you remember that from our Hardy-Weinberg exercise. At this point we can copy this through, and then once again if we change our parental population, you should see that the genotypes are not displayed if the individual is not part of the parental population. At this point we can summarize our genotype numbers, our genotype frequencies, and our allele frequencies for this parental population. And since you've done the Hardy-Weinberg exercise, you should be able to put the video on pause and fill in those cells now. Okay, let's count the genotype numbers of A1 individuals. We'll use the COUNTIF function. The COUNTIF function has 2 arguments. The first is the range, or the group of cells you want Excel to inspect, and here we'll choose the full range, cell C15 through C1014. And the criteria is going to be what's referenced in cell J3. And you can see that the spreadsheet is returning a 250. Let's anchor the range. And now we can carry this formula through. And what you should see is that these entries should perfectly match the entries you established in cell B3 through B5. From here, the genotype frequencies are easy. It's just the number of each type divided by the total. So the equation in cell J8 is going to be equal to J3 divided by cell B2. And if we reference cell B2 and fix it, then we can copy this formula through and our genotype frequencies are computed. You'll note that we've included some sum functions to just double check our entries. The genotype frequencies must sum to 1 or you've made a mistake, and the allele frequencies also must sum to 1 or you've made a mistake. Okay, how about the allele frequencies? How many A1 alleles are present across all of the possible alleles? Well, there's 1,000 individuals, and each individual carries 2 copies of an allele. So there are 2,000 alleles total. How many are A1A1? Well, that's going to be 2 times the number of A1A1 homozygotes, because each of those individuals carries 2 A1 alleles, plus the number of heterozygotes, because they each carry 1 copy of the A1 allele. We'll put that whole term in parentheses and we'll divide it out of our total alleles in the population, which is going to be 2 times cell B2. Make sense? The A2 allele frequency can be similarly calculated. That's going to be 2 times the number of A2 homozygotes plus the number of heterozygotes divided by 2 times the population size. And as a double check, make sure that those allele frequencies add to 1. So that establishes our parental population. And the next step is to let these individuals mate. And they're going to not mate at random, but they're going to mate according to the probabilities that you enter in this grid, cells E3 through G5. Let me explain how this works, and the easiest way to explain it is to simply enter some numbers and then I'll walk you through how we interpret these. So along the diagonal I'm going to enter 0.9 and then I'm going to enter 0.05 for the remaining entries. How you read this grid is you find the genotype of your parent, and you find that genotype in cells E2 through G2. So for example, we're concentrating now on individual 0 and their genotype is A1A1. A1A1's mate choice will be reflected down the column. So we're focusing down the column, and these entries represent the probability that an A1A1 individual will mate with another A1A1 individual, the probability it will mate with a heterozygote, and the probability that it would mate with an A2 homozygote. Note that these probabilities must sum to 1. So for example, according to these entries, if the individual is A1A1, it has a 90% chance of mating with A1A1, a 5% chance of mating with a heterozygote, and a 5% chance of mating with an A2. So it's not guaranteed that it will end up with any one of these individuals, but in doing so, we would expect that 90% of our A1A1 parents would end up mating with an A1A1 partner. The only time that non-randomness comes into play is if we set the entries as such. What does this mean now? This means that an A1A1 parent will only mate with an A1A1 genotype. Again, double check that those numbers result in the number 1. Let's set that back to where it was. And hopefully that makes some sense. Now we're going to use these numbers to create another tally. So our tally for parents of A1A1 will be stored in cells E7 through E10. The tally begins with 0, and here we're going to use that same kind of sum function, sum E3 through E3, anchor the first reference, and copy it through. For the A1A2 parent, we're going to sum F3 through F3 and anchor the first F3 and copy it down. And for the A2A2 parent, we're going to sum cells G3 through G3 and anchor the first reference and copy it down. So just like we had an array here, here we have a tally that begins with 0 and every single one of them ends with the number 1. And this creates a vector that is couched between 0 and 1, and we can use this to assign a mate. So for example, if I draw a random number and that random number is between 0 and 0.9, the mate will be A1, A1. If the random number is between 0.9 and 0.95, the mate will be A1, A2. And if the random number is between 0.95 and 1, the mate will be A2, A2. Make sense? So the first thing we're going to do is assign a random number for each of our parents, and that's RAND, open parentheses, close parentheses. And copy this formula through. Now you'll see that there are two columns, the preferred mate and the actual mate. The preferred mate will find that random number in the appropriate tally, depending on the parent's genotype. The actual mate will be the same thing as long as that genotype is present in the population. So if we say that A1A1 wants to mate with an A2A2 individual, but there are no A2A2 individuals in the population, we can stop that from happening by returning a missing value. And that is the roughest of cases where you don't get your choice, and so you don't take the next best option. We're going to also play with that notion in the sandbox as well. But for now, the idea here is to first establish the preferred mate down column E. Now this function is going to be a little tricky because we have to first identify the genotype of our parent. If it's A1A1, we're going to look up the random number in this tally and return the mate in cells D8 through D10. But if the genotype of our parent is a heterozygote, we're going to look up the random number in this tally. And if it's an A2A2 homozygote, we're going to look up the random number in this tally, each time returning the appropriate mate's genotype. So we need an if function and some lookup functions to make this return the correct answer. And to do that, first we're going to choose the lookup function. We want the lookup function that has 3 arguments, And we're going to be looking up the random number in a lookup vector. And here's where it gets a little tricky. So let's skip this right now and head over to the result vector. The result vector will be the mate choice, so we can go ahead and populate that with D8 through D10. The lookup vector, though, changes depending on what our parent's genotype is. So here we're going to embed 3 if functions, or 2 if functions, to make sure we identify the correct lookup vector. So let's head over to the if function, and we'll say that if the genotype is A1A1, and notice the quotes here, then our lookup vector is going to be E7 through E10, and we'll anchor those. If not, we need another if function. The first logical test is going to be if the genotype is equal to A1, A2. If it's A1, A2, our lookup vector will be cells F7 through F10. And if it's false, our lookup vector will be cells G7 through G10. These need to be anchored, and we press OK. And here we have our full equation. A little bit complicated, and if this is not easy for you to do, you can always add some columns to your spreadsheet and break this formula up into multiple pieces. I've kept it as one equation simply so that I can show the whole screen on the video. If all goes well, we can copy this through, and our equation will have been populated correctly for each and every individual in our population.